Please don't mind the stupid bird. We'll see that window capture in a minute. I'm in the process of checking out an generator. Maybe we can zoom in here. I don't know, this thing's not focusing right. Oh, there we go. So I got this little generator down here in the pile. It's like right there. There's a bunch of little white buttons on it and stuff. And I'm monitoring the waveform on the scope here. Can't see it very well. I don't have the trace slowed down. Oops. There we go. So I didn't think it worked actually, but I'm telling you, I got the amplitude cranked. It's the 600 ohm output, and I have the amplitude cranked way down. It's sitting around 2 kilohertz. It's 1 kilohertz, and then it goes up to like there's 1 to 10 kilohertz right there. But the amplitude on this thing is unbelievable. This baby cranks. It even goes into distortion. Like, it starts getting distorted right around there, so that's probably the best discernible signal. And that's like almost 2, 4, 6, 8, 10, 12 volts peak to peak. That's a major ass sine wave. I mean, I would not want to have that much power. But I didn't think it worked, and there's other functions on it. Well, it doesn't have a ramp generator, unfortunately. But let's check out these higher frequencies. It goes up quite high. There's 10 kilohertz. I mean, there's that's 10 kilohertz up to 100 kilohertz right there. It's a little, you know, it's got some shaky stuff going on, but for all intents and purposes, and that's putting out, that's like, look at that amplitude. Oh my god, that is huge. I just got this stuff for practically nothing. Now I'll put it up to the 100K. Okay, that's got a problem there. I don't know what's going on with that. Okay, just a bad connection on the 100K, but it puts out, that's like 1 megahertz right there. Let's crank it back down to the 1K. And, oh wait a minute. I guess that's 1K to 10K right there. And we can verify that. You can't see my generator up top there, can you? Oh, I mean my frequency counter. I mean that's my frequency counter is right there. You can't see it. I wanted to get more emphasis on my circuitry and my drink. So that's reading, I guess, 6 kilohertz. And that's about what it's setting on. 1 kilohertz right there. Now it says, I never can read that dial. On this other counter I could read, it says 10 hertz, 100 hertz, that's the resolution. So the resolution is 1 hertz. I mean it's reading 1029 hertz. So if I do a resolution of 10 hertz, that's 1.02 or 1.03. That's my lovely bird doing that. He likes to get a word in edgewise. And then if we go to this other one here, I don't know what that means. It's not doing anything. There's actually a 0.1 hertz resolution. Let's drop it down here. See if I can read this 0.1 hertz resolution. Yeah, I don't know. I don't need to be that sensitive as long as I know I'm in. You know, the idea of where I need to be. There's 10 kilohertz. I wonder if it'll read up to the 100. Let's see. There's 60, 75, 104. That's 100K. 300K. 600K, 800K. It goes over the 1 megahertz. That's pretty cool. That's an 80 megahertz. It goes up to 80 megahertz, but this generator only goes up to 1 megahertz. And I found out that my scope, my second channel on my scope, seems to work pretty good. So there's that. Let's see if it'll do a square wave. And that's a distorted square wave. Oh, you know what? My second channel on my scope has a distortion problem. I'll check that output on my channel 1 on the scope. That's pretty messed up right there. Let's check the triangular wave here. It's not too bad. And this goes down to 100 hertz, so I can really get down to low values of hertz with this machine. That's 200 hertz, and the value is going up because it's should be a 600 ohm load, but what are you gonna do, you know? Look at the amplitude on this thing. It's humongous. Now we're reading down into the 10 hertz. That's 10 hertz. Up to 100 hertz. Now I'm reading 10 hertz down to 1 hertz. Look at the amplitude on these sine waves. Oh my god. That is just unbelievable. It's like this baby cranks like crazy. Let's go back to the square wave. And we can see there's quite a bit of distortion there. I mean, that's, yeah, when I crank the amplitude, it's quite distorted. So let's see if the channel on my others, well, that's actually reading AC, isn't it? It's still distorted. And there's the DC offset, where I can raise this above and below DC on the output. That's pretty cool. Now let's look at channel 1 on my scope here. Well, that's definitely looking a little better. I really have to crank the amplitude down. So, I mean, I could, yeah, the amplitude's like gotta go way down. Oops. Let's get good sensitivity. Now see, if I crank it up too much, it gets distorted. The square wave gets distorted. That's 10K right there. That's 1 kilohertz. Oh, that looks pretty good for a square wave. Oh my gosh, look at that. You know, I can't complain about that. Well, I'll take that generator maybe apart and just clean it up or something. I don't know why the output... It would be nice if the output level stayed constant when you change the frequency. It doesn't seem to want to do that. There's 1 hertz. So this would make a pretty decent pulse generator, only for a 50% duty cycle. And it doesn't have a ramp on it. It only has a triangle wave. Let's see what that looks like on the upper frequencies. Looks pretty steady. That's a nice sawtooth wave. I mean, we're talking, that's like almost at its lowest setting. That's like 1 volt peak to peak. I mean, that's just ridiculous. There's 1 megahertz down to 100 kilohertz. Now let's look at the square wave again. It's a sine wave. That's a little distorted. Oh, if I touch the box, it's, oh shit, something's screwing up here somewhere. I don't like that. It's doing something bad. Oh, it's the switch. It's the 100K switch. I don't really care too much about, well, that's 500K. It's not so bad. It's got a little distortion in it, but it's a good signal. It's a good enough signal to measure, like if I wanted to send a 500 kilohertz low-level signal into a circuit. I mean, look at this amplitude. I mean, I could crank the amplitude up a little bit and then drop it with the attenuator. I might look at that output on that attenuator on this thing and see how it works. It's got some distortion in there. It's not a really good looking square wave. It's rounded at the ends. Maybe it might need adjustment or something. There might be a calibration thing in here for this. Not too shabby. That's 60 kilohertz right there. Up to 100. Back to 1K. The knobs are a little bit off kilter. Not so bad. I wanted to build, there's a little basic oscillator circuit with an LM324. I wanted to build that on the board. Well, I'm somewhat happy with that, I guess. I will turn that off and unplug it. I'm not ready to run that constantly yet because it looks like it needs cleaning. But actually, at first, when I looked at this, I didn't know how to hook it up because I didn't understand the input thing on here. So if we look at this, and it just fell apart, but if we look at this generator, it's a 310 Dynavision function generator. It's just it's a pretty basic square wave, triangle wave, sine wave, 1 hertz up to 100 kilohertz, 1 hertz up to 1 megahertz really. And these little input things, I can't get this over there to show you. These input things here use a BNC to TNC, I think that's what that adapter is called. And there's a 600 ohm on here, and so you just hook that up like that, and that's what that looks like for the output. The ground is backwards because I just hooked it up backwards. The ground's in the middle. That wasn't too bright. Did it blow it up? No, it's not working. It's not turned on. So this works. I didn't know that. So I will just put this aside for now. I want to plug in the pulse generator. And see if that explodes on me. This just has a BNC output, and I will connect that to my scope before I turn it on. And somehow I did not run the plugs here, did I, for that machine? I don't know where exactly that is. Oh, there it is. So that's turned off. I got that everything on that outlet strip is plugged in, but the radio's plugged in, but it's not plugged in actually. It's not being used. Alright, let's see if this baby smokes. Now, this thing's a little bit more like it's got some contact issues, but it's a pulse generator. It's not a square wave generator. I can vary the duty cycle. Now, if my hand seems to be in the way, right? So if you look at that waveform, what I'm doing is like right there, that's probably like maybe a 10% duty cycle. Where now if we look at this very carefully and go to the ground and set the ground on the 0 and put it in DC, it's acting below 0 volts, so it's in the negative. So let's see if we can get the pulse to the positive. And now there's a positive leading pulse. This guy is right in my way, isn't it? Right, so some shadow there. Now I can adjust the pulse width, duration, the duty cycle on the top, and as you can see that gets bigger. And a square wave is 50%. Now it's got issues, you know, but we can really get this thing narrowed down here if I can. I can't trigger that. There's the trigger. See, there's a very it's a 1 microsecond pulse right there, and the frequencies, you know, whatever the frequency, the period is set to. It's a higher period, 10 microseconds period, 100 microseconds. So there's a very narrow pulse in there. There's a 1 microsecond pulse at a period of 100 microseconds. So that's 1%. That's a 1% duty cycle, I guess. That's 1 microsecond for every 100 microseconds. And you can't even see that in there, actually. You can't even see it, but I'll back off the. You might be able to see that in there. And the amplitude's like cranked way down. Again, as usual, for some reason. That's like 1.5 volts right there. So you can barely see at the end over here, there's a very narrow pulse above DC. And I can vary the width of that pulse. See, it's even longer. And then it adjusts the. Now that's 100. And if it goes too far, if it goes over the period, the little light will come on and say the pulse width is greater than the period. It'll just say that's an error. So the reason why we want pulses in let's say that we get a signal. Let's say that our normal signal is like, well, we get a normal signal and it's a 1/2 volt peak to peak. What if we get a signal that's a very narrow signal and it's higher than 5 volts peak to peak? If we're averaging out all of our input and we have filters in there to prevent transients from getting in, we want to see how fast the circuit responds to a transient, because a transient pulse, it's not really based, it's based more on, I think, DC voltage, like a voltage spike versus a frequency. So it could have an effect on the circuit. So we want to check some of that. We want to check those things. Now I'm gonna. That's the idea behind that pulse generator. I'm gonna shut this off because I sort of don't trust it, but it's actually working, and I want to just, you know, I only want to use it when I need it. Now let me think. Okay, I'll just put that there. I'm going to go over to here. Let's just back the zoom off here. We're going to go to the website here. Now there's this circuit that's a little bit complicated looking. I don't know if we can build this or not. Regarding chaos theory and the chaos, this is sort of an this will be an introduction to chaos theory. Basically what that is, let's say if we look up, let's see, let's go to YouTube. Get my earphones on here. We're going to go, it's easier to go into some of this stuff on YouTube because some of this stuff has already been done. But we want to talk about, and there might even be some chaos series circuits already built up on YouTube, and we want to be able to repeat those. But we're going to do something with them that nobody's done with them yet, so that's what we're trying to figure out here.
Hey guys, check this out. I'm really excited today because I found something I had no idea existed. It's the negative resistance region of certain transistors when you bias them in a certain way that you can utilize to make a very simple single transistor relaxation oscillator, such as this one right here. Just got a blue LED flashing at low frequency, but let me first explain how this came about. I started out with this box of transistors right here.
Oh,
they're
God. Look at
SWB
look at all those metal
2433, and this is the paper that came with the box. There was no other documentation, and apparently Texas Instruments themselves don't have any documentation for this thing either. They say it might be a custom part, so really the only way to learn about them is to throw them on a curve tracer like I have here. So I have actually two transistors on the curve tracer. One is the SWB 2433, and then a just ordinary 2N34. Wait, yeah, 2N3904, very common small signal transistor. So I got that on there, looking at the SWB, and in the forward bias region, very normal curves going on here, very typical to the 3904. You know, very basic stuff that you learn about in your basic electronics course in your textbook and everything. But in the negative region here on the SWB 2433. Look at that. Goes negative and then shoots back here. We have voltage on the horizontal and current on the vertical, and so that's negative resistance right there. Now the 3904 does not have any negative resistance here in the negative region, but if I just make a quick change, I'm going to reverse bias both of these and leave the base floating. Okay, so now I just got current going into the emitter and out of the collector of these two NPN BJTs, and we're looking at the 3904 and the SWB, and you can see they both have a negative resistance region. Here's the origin, the 0 point, and so voltage, it won't operate for any voltage or any resistance. The capacitor, however, you can put just about any capacitor you want. That all depends on what frequency you want with this half hertz oscillation here, approximately 1 pulse every 2 seconds. I got a 1000 microfarad cap, and of course if you want higher frequency, then you just put a smaller cap in there. And then you can see how it operates here. The voltage source charges the cap through the resistor until we reach a certain point where the transistor starts to become conductive. It goes from open circuit to almost a closed circuit with 4 volts. Okay, I zoomed out here so you can see the whole setup and see the range of operation here. We're at, again, with the 2N3904, flashing that LED down there, and I'm at 15 volts. Let me turn down the voltage. So at about 14 volts is when it stops flashing. And turn up the voltage. Frequency goes up. And it's actually still works pretty good, even up to 25 volts. Still flashing all right. And a much higher frequency too, at about 10 hertz or so.
So before we get into chaos theory, we probably want to look at transistor oscillator theory.
Hello dear student, here is the new concept of physics, and in this class we are going to learn a very important topic जो कि हर तरह के बोर्ड एग्जाम्स में 101% important माना जाता है. And today's topic that we are going to learn in this class is transistor as an oscillator. In the previous video, we have already discussed all the things related to this transistor, how these transistors are made, generate electromagnetic wave, but that type of wave is not important for communication perspective because they get lost after covering a certain distance. तो हमें चाहिए undamped wave. अब ट्रांजिस्टर की वो खासियत की हम बात करते हैं, तो ट्रांजिस्टर में दो तरह की कैरेक्टरिस्टिक है. वन इज इनपुट एंड अनदर इज आउटपुट. और अच्छी बात यह है कि दोनों को मैंने अपने दोनों वीडियोस में अपलोड किया ही है, ट्रांजिस्टर एज अ स्विच और ट्रांजिस्टर एज एन एम्पलीफायर. आप उसे देख करके इसे समझ पाएंगे. फिर भी एक बार हम फिर से यहाँ पर समझ लेते हैं. इनपुट कैरेक्टरिस्टिक इज एक्चुअली द ग्राफ ऑफ इनपुट करंट डेल्टा IB and input voltage delta VBE, while output characteristic is the graph of delta IC output current and output voltage delta VCE. For the input characteristic, we see that whenever we increases the voltage, current 0, whenever we increases the voltage, current 0, increases the voltage, current 0, but after certain a voltage current gets start. कुछ वोल्टेज के बाद करंट स्टार्ट होता है, ऐसा क्यों? बिकॉज ऑलरेडी ट्रांजिस्टर के अंदर पी एन जंक्शन है, देर इज ऑलरेडी पोटेंशियल बैरियर, देर इज ऑलरेडी कट इन वोल्टेज, सो यू हैव टू प्रोवाइड मोर वोल्टेज कंपैरिजन टू कट इन वोल्टेज इन ऑर्डर टू स्टार्ट द करंट. करंट को स्टार्ट करने के लिए हमें पोटेंशियल वैल्यू, हमें हमेशा पोटेंशियल बैरियर से ज़्यादा देना होगा. तो ये स्टेट क्या है? दिस स्टेट इज कॉल्ड कट ऑफ. और ये स्टेट में क्या होता है कि इनिशियली वी इंक्रीजेस द वोल्टेज, करंट इंक्रीजेस, बट आफ्टर अ सर्टेन पीरियड करंट बिकम्स सेट. देखिए कलेक्टर करंट सेट हो गया, अब ये कांस्टेंट है. अभी आप वोल्टेज को इंक्रीज करिए, इंक्रीज नहीं होगा, खुद को कांस्टेंट रखेगा. ये क्या है? तो दिस इज कॉल्ड सैचुरेशन करंट. तो ये सैचुरेशन करंट क्या है? अगर हम वोल्टेज को इंक्रीज करते हैं, दैट मींस इफ
I got distracted. Why am I getting into this Indian freaking topics here? Jesus. Fuck. Now there's two things happening. Number one, the chaos waveforms are mechanically created, and the signals are combined together for display on a scope. Or number two, they are electronically created by causing a circuit to go into oscillation, thereby feeding back into itself, causing it to generate random signals. I don't know. I just wanted to make that stipulation because I think there are going to be people here that are just creating the waveform, but they're not building a circuit to let the waveform create itself, which we'll talk about in a minute. No, I don't know. It's not helping out too much.
Hello, we'll be hooking up a chaotic circuit to an analog scope. Let's turn the scope on. Hook up the probes. One goes to C1, the other one goes to C2, and of course connect ground here and here.
So he's using direct probes.
Make sure we're in the XY mode on the scope.
XY mode.
Let's turn it on. Let's change the parameter. As I turn, here I have a simple oscillator, first bifurcation, and chaos.
Oh god, that's nice.
Let's make this a little smaller so we can see better what's going on. I'm going to change the other parameter.
Now see, I don't know if... Okay. I don't know if he's... I think what he's doing is he's got the two oscillators and he's combining them. He's not... I don't know what he's doing, to be honest with you. It says hooking up the Chua circuit. He's saying that he's actually doing the Chua circuit. Let's see what he's got here. Ew. let's see, we're gonna guess at what he has. So there's two circuits here, each with its own oscillator, and they are connected by this resistor. This looks like the circuit that I want to build. This is cool. This is cool. Okay, so on the right, or on the left is the Chua, what's called the Chua diode, and on the right is what's called the gyrator circuit. Now, we'll go back, and before we go into his briefing on that webpage, let me see if I can find the circuitry. Okay, this circuit right here. So on the left we have what's called the Chua's diode. That is there's some theory behind this. You can use a regular inductor and a capacitor and some other equipment. There's other components, and make some negative resistance amplifiers or whatever. There's theory behind that. We'll talk about that in a minute. I don't want to get into too much with the theory, but anyway, this is an example of the circuit that he's building. It looks like the same circuit. Now, A1 and A2, A3 and A4, let's see if this is figure 3. See, now I don't know. This is full text available. Okay, here's the Chua diode portion of that circuit. Let me just skip down here. Okay, this looks like a very good explanation of what's happening. Nelder-Mead simplex method and representation of new points in search space. So in other words, this is an area where the circuit's looking for something. And those are restraints, X1, X3, and X2. They could be restraints. They're talking about fuzzy modeling. I'm not going to get into all that theory. Here's some basic theory here. This is back in 2000. This is 20 years ago. C times dVc1 over d2, which is the change in voltage over time times capacitor C1, equals the change in voltage differences of C1 divided by R11, which I'm not seeing on that down there, equals the current through the diode, or minus the current through the diode times VC1. This is modeling of the diode itself, where R11 is a linear resistor, L is an inductor, VC is the voltage capacitor, and IL is the current to the inductor, The static nonlinearity of Chew's diode is the piecewise linear curve given by current that passes for the Chew's diode as described, etc. And there's a formula there, where M0, M1, and MP are the parameters. The nonlinear characteristics can be realized using operation amplifiers. It is worth mentioning that different values for the components of the electric circuit result in attractors with different geometry. Now, what these are negative impedance. I can't remember. Let me see if I can find that information. Just stay with my thought for a minute here. I don't know if I have that information. Okay. In electronics theory and chaos theory, Chew's diode is a type of two-terminal nonlinear active resistor which can be described with piecewise linear equations. It is implemented as a voltage-controlled nonlinear negative resistor. That's the emphasis behind it. Okay, so remember this fellow was talking about negative resistance in that transistor, the way he had it set up there, like backwards or something. An ordinary resistor which increases the applied voltage across causes a proportional increase in current due to Ohm's law, resulting in a positive resistance. In other words, let's say you have a current going through a resistor. If that resistor goes up, the voltage across the resistor goes up, because you're reading the voltage across the resistor. The current could stay the same. If the current goes up, E equals I times R is Ohm's law, I believe here. Now, this is the actual formula, I equals V over R, but I don't remember it that way. I remember it as E equals I, it says E equals I times R. The voltage is the current times the resistance. So if the voltage goes up, if the resistance goes up, the voltage goes up. If the current goes up, the voltage goes up. If the resistance goes up, the current goes down. Well, usually you do it in terms of current. I don't know. And then you've got P equals I, E times I. And I equals, I don't know, I squared times R equals P or something. I don't remember the stupid numbers. But anyway, I don't like to get into that. This is a difficult concept to understand. How do you get a negative resistor? Well, a thermistor might be an example. Let's see. If it is negative, the resistance decreases with increasing temperature. It's called a negative temperature coefficient. It's sort of an idea, kind of gives you an idea. Like a thermistor has a resistance, and if the temperature goes up, then the resistance is going to go down because it has a negative effect on the temperature. That's sort of an analogy. It doesn't really apply here, but there's just theory behind it. For all intents and purposes, you can create a negative resistance with op amps. So here's an example. You have your negative impedance converter. So according to the information to a circuit, they took two of these and made them back to back. So let's see. Where did I see that circuit now? God, I can't find the circuit now. That's this guy's. I had to go look for it again. No, I'm not as organized as I should be. Okay, so it's that PDF. It talks about Jewish diet. Let's just move this over here. Alright, so we've got a resistor in the negative feedback, which is the minus, and a resistor from minus to ground, and we've got a resistor in positive, and the signal, but the voltage signal source goes into positive. I don't know where they're calling this a negative. IS is negative. Rn is equal to minus R3 over R1 over R2. That's the change. I'm assuming that's the change in resistance across the terminals, maybe. It could be what they're talking about. So here we've got your minus. Let's look at one half of this circuit. You've got your minus resistor, and then you've got that resistor minus is tied to ground. You've got minus feedback, and minus is tied to ground. Minus feedback, minus is tied to ground. And then you've got a plus resistor. There's the plus resistor with a voltage source attached to the plus resistor. And then here is another one, okay? So they've got two of these back to back for whatever reason. However they decided, why would they decide to do that, you know? If you can put two back to back, why not put an infinite number of these back to back, you know? There's this idea about synchronizing Chua circuits. Now there's a section in the middle that connects the Chua diode to what is called the simulated inductor. The inductor is simulated by what's called a gyrator circuit, which is kind of interesting because we were talking about this in the ELF receiver that we're going to build. Now let's look at this pi circuit. Okay, so we sort of have an understanding about the Chua diode. They've got two of these negative impedance things connected together. Let's go all the way back here and let's see if we can find that. Let's see, there's another circuit down here that's simulates some stuff. I went through all of that. It's kind of an interesting looking circuit. Okay, this bubbling, doubling root to strange whatever. See, here you've got two capacitors. This is what's connecting the Chua diode to the other thing. So I don't know exactly that conversation is. This is a low pass filter. So if we go to if you look at a low pass filter, let's do so in some of my previous talks we talked about impedance matching. There's this wine bridge oscillator I wanted to build. There's an example of a band pass filter here. You've got a high pass section and a low pass section. You combine the two together and you get a band pass filter. I don't see. I don't see an impedance bridge. This is a power supply filter. I guess I'll have to explain it. So, in other words, if we go back to, we'll have to jump ahead, but if you look at this circuit, it's, okay, now this gets into what I was looking for. If you look at the impedance from left to right, you have a resistor capacitor combination in parallel with a capacitor. If you look at the impedance from right to left, you have C1 in parallel with a combination of R and C2. Now if C1 and C2 equal each other, the impedance is the same. But what if you have, let's say if you have an output impedance of a circuit that measures, say it measures 100 ohm. Well, say it measures 600 ohms, and you want to match that to a circuit that has an input impedance of, let's say, 6 megohms. If you connect the two circuits directly together, the input circuit with a low input impedance will load down the amplifier, because it'll load down the input of the amplifier, which is probably okay. But the ideal situation is to match the input and output impedances. So the way you would do that is you would have this RC combination here, the R and C2, would equal 600 ohms. Wait just a minute. The combination of R and C1 in parallel with C2 would equal 600 ohms. And then the output would be the combination of C1 and R and C2 in parallel would equal 6 megohms. That's what you're trying to do there. So that's a little bit complicated. But so here's another circuit. You can see the inductor here. I didn't go over this earlier. And then you've got C1 and C2. Figure 1 realization of quasi periodically forced Chewers circuit. Here NR is Chewers diode, and we talked about that. That's your gyrator circuit. And on the left is the negative resistance bridges. The parameter values for the circuit elements are fixed. C1 is 16.8 nanofarads. C2 is 98 nanofarads. L is 18.75 millihenries. R is 1,565 ohms. G, that's inverse resistance, I think. I don't know. Those are values. The frequency used was 2.849 kilohertz. So, and the other frequency is 3560 kilohertz. So there's two frequencies here being generated. The forcing amplitude F1 is taken as control parameter, which is being varied in our analysis. Now, if you look at here, we can define the parameters for the equations. dx dt equals alpha parentheses y minus x minus h of x. These formulas are defined by, well, you have this formula and you have dx dt. You can go back to the circuit parameters and come up with dvc1 over dt times c1, which equals dx dt, and then you relate the Chewers diode values for the values in the Lorentz circuit, the mathematical circuit itself, and that's how you figure out your components, I guess. I don't know how they managed to figure this stuff out. This is supposed to be a period doubling route to chaos. You can see the bifurcation diagrams here. You can see how certain things are happening. This is cool right here, this log of x over RE of x. It's like these little dots are formulating. strange attractors that are not chaotic. Research gate. A strange attractor is not a finite set of points, and it is not a piecewise differentiable, which is what they're using in those formulas. Like, I sort of understand what they're saying. It's acting like a repetitive system, but they're saying, but there has to be this sensitivity to initial conditions to get it started. It's possible that that circuit is not setting up initial conditions. I don't know. Now there's some circuits here that I picked off from somewhere. And I don't remember where I got the circuits. This first circuit, this is a complete example of a Chua circuit, or diode. The two diodes are part of it. This is X, this is the first derivative, which is negative, and this is the second derivative. I don't remember where I got this image. Slideshows.com, strange attractors. I'm assuming these are complete circuits here. Now this looks a little bit more of a familiar type of a circuit. We can see the Chua diode on the right. So on the left would have to be the impedance things. There's two capacitors here. Resistor. Plus voltage to the collector. And here's an inductor. I don't know. I don't understand that. I don't know. A multi-scroll chaotic oscillator circuit, as shown by that diagram. PWL function to generate behavioral model of chaotic system can be written in terms of a state variable equations. These are derivatives. This is dx dt, dy dt, dz dt, and these are combined in such a way as to produce a three-dimensional figure on a scope. And the way that is done, this fellow designed a device to create a simulation on a scope. I'm wondering if you can't use the three colors.
Hey there! So, yes, this is a piece of crap television. I found this on the side of the road, and why am I even showing this thing to you? Well, let me tell you a little bit about it. It's an LXI series. I think this was sold by Sears and Roebuck here in the United States, but it's actually made by Funai, which I think is a Japanese company. Anyways, very, very low-end TV. It's 19 inches, and it was just left in the dirt. Made high whenever there's an RGB signal that needs to be displayed. So the other chip will essentially show the regular TV picture, but as soon as this line goes high, and with them, it will show whatever's coming in on the RGB, and you can actually, you know, that way you can show graphics that are overlaid on top of the NTSC signal. But typically, if you pull one of these high or low, I can't remember which way it needs to go on this chip, it will either show only the NTSC signal or only the RGB signal. And when you watch this on the oscilloscope, you'll see a pulse, you know, that matches up with the text. There's another problem as well. So, because this television has the RGB, did you notice there was no sync signals coming in from that other chip? It's basically just input into here using RGB. I can't remember, I think fast BLK, that's pin 30, that is the one that's connected to the output on the other chip. So this is the one that blanks it and switches to the RGB input. Notice there's no sync input here, and normally not a big deal. You would just use the video input on your TV. Say if you're using a PlayStation console, you would hook the video composite up, and that would send the syncs, and then you could use the RGB to essentially show the screen. But this has RF channel 3, and short of using an RF modulator, I gotta figure out a way to get the composite input onto here. So on some TVs, the TV tuner, that's the video or the RF input, actually just outputs a composite signal right out of the tuner, and that's what goes into the video chip. So you could just hijack that signal, obviously, and then input the composite signal directly into the video chip. But on this TV, for, you know, ultra cost reduction, the tuner actually outputs an IF, an intermediate frequency. So essentially whatever channel you pick, it brings that frequency down to like 54 megahertz or whatever the IF is, and then the main video chip does the processing. So looking here at the block diagram, this is the IF section of the chip. So see, it says VIF in, that's the video intermediate frequency in, and there's all this stuff here, and it results in a composite output. So essentially, you could draw a line through here, and this section of the chip that does the IF, which is frequency conversion to a composite signal, is completely isolated. And what's cool about that is that means that this video output isn't just used to say output like to a possible video out connector on the TV, but it actually loops around and is connected here to the TV-Y input here. So this section is the video switcher, and see, here's where it has external video C in. This is what's not connected, and there's a bunch of components missing, but TV-Y in is actually connected through to this video output. So that's perfect. That means I could just cut the signal that comes out of here, use the passive components that are on the board, like because this requires a capacitor and stuff like that. I could use these, but I'll cut the trace, and then I'll solder into the middle, and hopefully that will give me a video signal. Okay, so here's the main video chip, and I'm not going to go into too much detail because every TV is going to be different, and you know, it's very unlikely you're going to run across this exact TV. But essentially, looking at the pinout, the video output from the IF section is up on this part of the chip. And actually, I put a little black dot on the board right here. This is where the video output signal was found. You know, I could trace it out, goes through some passives and over somewhere else. I don't know where, it doesn't matter. So what I did, and it's going to be hard to see, is I used my knife and I actually cut the trace right here.
Wow.
So I did that because I wanted to poke around and just kind of see where the best point to inject the video signal might be, because you know, this needs some passives to, you know, bring the signal in appropriately into this chip. So I wanted to kind of poke around through the video path and just figure out where it was. Now, the video in on the block diagram is actually right here, and it may be hard to see, but it actually says, I'm having a hard time seeing, TV in right here. So they hardly labeled anything on here, but they actually labeled TV in. This is a little jumper link on the other side of the board. This, if I tested with the multimeter, is actually the input into the chip. And it goes through a capacitor here, and then it goes through another capacitor. And you can see this green wire soldered here. This is actually where I ended up putting the video composite input. So this RCA cable here with clip leads is coming from my video test pattern generator. As you can see, it's connected to this green wire I have soldered on the board. The ground is connected to a ground wire here that I have soldered onto the board down there. And if we go to the TV on the front, actually let me turn it on. Oh, let me plug it in because I had it unplugged while working on it. Don't want to kill myself. Turn on the television there. And let's go take a look at the other side. All right, here's the TV, and it's funny. You see it says 3, like it's in channel 3. Well, I'm currently showing a black picture. Let's put this on. There we go. There it is, SMTP color bars. And, yeah, it's pretty darn great. And, of course, the funny thing is, because the tuner is now bypassed, even though it says channel 3, if I switch the channels, the number will change, but nothing actually changes on the screen. So we're getting a nice, sharp, NTSC interlaced signal here. Yeah, not bad. I mean, I don't love the color balance here on the NTS signal, but it doesn't matter. I'm not actually going to be using this. I mean, I guess I could for, like, say, Nintendo or something. I connect it to the 1.38 volts. There we go. We got just the menu. So right now we're looking at a pure RGB signal, meaning this is what we're going to use when we want to look at the switch over the wire. That's my multimeter shutting off. I'm switching over the wire, the gray wire, which is the one that does where the
to help enlist the trust of all their newly acquired employees was to give them all a gift. And we had the option of receiving either a little TV, like this one, or a VCR, or a microwave oven. I actually opted for the TV, and it's actually been a really fantastic little TV. Now, I want to point out that when I first received this, it was 1997, and I was 22 years old, and I was living in a one-bedroom apartment with my newly married bride. Well, at the time, we didn't have a lot of money, and this actually became our bedroom TV, and we actually watched TV on this. I mean, this little 13-inch TV, it's hard to imagine, but this is actually what we watch TV on every evening for probably a couple of years. So for the last 15 years or so, this has become essentially just a monitor for me. I don't really use the TV part of it anymore. In fact, I couldn't even if I wanted to, because analog TV doesn't exist anymore. But it makes a really good little composite monitor for hooking up to a Commodore or a Nintendo, an Atari, or something like that. And but it has been brought to my attention repeatedly over the last several months that it is actually possible to mod consumer televisions like this to display an RGB signal, specifically an analog RGB signal. Now, why would I want to do that? Most every computer made since the late 1980s has either supported some sort of RGB video signal or just flat out required an RGB monitor. However, there are a variety of different standards. So the Amiga, for example, used this 23-pin connector, and the Apple IIgs used this 15-pin connector. IBM CGA and Tandy machines used a 9-pin connector. And of course, VGA is also a type of RGB signal as well. An RGB signal typically consists of 3 separate wires carrying the red, green, and blue signal. There's also typically a sync signal and a ground. Of course, any color CRT television has to break the signal into RGB at some point, because that's how it's delivered to the back of the cathode ray tube. However, that's a high voltage signal at the back, so ideally you'd want to feed the RGB signal somewhere on the low voltage part of the board. So let's take this one apart and see what we can find. Okay, this is all pretty standard stuff for a TV from this era. First thing I'll want to do is discharge the tube. This spring appears to be connected to the DAG ground, so I'll attach my alligator clip to that, and I'll attach the other end to a screwdriver, and I'm not really expecting anything since this has been powered off for days, and most TVs from this time have a discharge resistor. And yep, there's nothing. I'll go ahead and remove the suction cup, and now I'll just need to start unplugging things. I'll start with the tube itself.
This is a good video.
And eventually the board will come out.
He's brave.
This thing's a bit dusty. I'll go ahead and hit it with some compressed air.
He's brave.
Okay, so looking at this board, there are only two chips we need to focus on. One is this microcontroller. And this chip drives the on-screen display, tunes channels, listens to the remote control, etc. This other chip here is what is commonly referred to as a jungle chip. And almost every TV from this time period has one. And this chip does most of the signal processing. Now, one of the things the jungle IC does is to take the composite video signal and then decodes that into RGB and outputs it to the high voltage part of the TV. However, it also accepts a direct RGB signal from the microcontroller for the on-screen display. But in order to know when to switch to that, there's another line called a blanking signal, which the microcontroller will output when it wants to use the screen. So what we need to do is tap into this RGB signal here and take that to the back of the TV. And then we need to locate 5 volts somewhere on the board and run that to a switch at the back of the TV that we can use to force the blanking signal whenever we want, so that the RGB signal will override everything. There's still one piece of the puzzle left. You still need to get sync from somewhere. Well, we can just use a regular composite input for that, because the jungle chip is designed to overlay the RGB on top of an existing signal. So we'll still be looking for the sync signal from the composite input.
Okay, so that's the rough explanation of how this works. Now, I'm not going to go into great details about resistor values and stuff like that because every single TV is going to be a little bit different. In fact, analog electronics is not exactly my strong suit. I actually got a lot of help from a guy named Mark Cohen who looked up the schematic diagram for my particular TV model, and he actually helped me figure out which resistor values I needed for mine.
Now, let's get to modding. One of the first things I'm going to do is place a jumper wire across this resistor. And I'll be honest in that I don't fully understand why I'm doing this, but I was told it would improve the picture quality. And this has something to do with the closed captioning circuit where it dims the background around the text, and apparently we want to turn that feature off, and that should do it. Now, these 3 resistors here are the red, green, and blue lines, and their purpose is to lower the voltage coming from the microcontroller to the correct input voltage for the jungle chip. Now what we need to do is add another 3 resistors in series to these, like this, and then we want to run our external lines in between them, like this. So the way I'm going to do that is I'm going to heat up the legs on one end of these resistors and pry them out, and then I'm going to straighten the leads on them. I'll use some desoldering braid to soak up the solder and open those holes back up. Then I'm going to take these 3 new resistors and I'm going to put those in the same holes, like this. And then I'll solder in those resistors from behind. And so what I've done is connected the resistors together in 3 little triangles and soldered the wires to the top of the triangle. And I'm putting some heat shrink on just to make sure they never touch each other. And there we go. There was also this unused connector port on the board. Not sure what it was going to be, but it has a ground available. So my 3 signal grounds are going to connect here. And there's also a 5 volt signal in this same unused port. And so I'll connect that to our little blanking switch. And I'll just solder these in from the back. Then we need to connect a wire to the blanking pin on the microcontroller. That's where our 5 volts will go when the switch is turned on.
Oh,
it's pin 25 on this chip, so I'll just put some solder on the leg here, and then I'll come back and just solder my wire directly to it, like so. Believe it or not, that is all of the modifications that need to be done to the board itself. So I'll go ahead and reassemble everything for testing. Now I have this really long ribbon cable coming out of the back of the TV, but for the moment I just want to find out if the TV is still working after all that I did to it. So I'll connect up the Apple IIgs from the composite port, and hopefully the TV doesn't blow up or anything. Well, here goes. Okay, no smoke or anything, so that's a good sign. I did notice the on-screen display is a little dimmer than before, and I think that was to be expected with the mods that were made. But it is still plenty readable, so that's fine. Let's power on the Apple IIgs. And we have a picture, exactly like it should be. Okay, all good so far. Next, I want to do a quick and dirty hack here to test the RGB. So I've taken the ribbon cable and wired it straight to this 15-pin connector. I've also just tied the blanking wires together. So I'll plug this into the back of the Apple IIgs, and let's fire it up. And to my amazement, it worked first try, and the signal is amazingly clear, although my camera isn't cooperating since the polarization is causing a moire pattern on the camera, but I'll try to get some better close-ups later. But for the moment, I'll just run through these colors to make sure everything is correct, and it is. I'll also set it to 80 columns for a quick test. Typically 80 columns on a television is unreadable. However, it is very readable here. Again, I apologize for the moire pattern, but you'll get some better footage later. So what I need to do now is figure out where in here I can mount my connectors. And I want to mount this switch and these 3 RCA jacks. And the trouble is, if you look back here, there's a lot of stuff potentially in the way. And I definitely don't want to have the wires or back of the jacks bumping into these heat sinks or the flyback or anything else. So now there's actually space on the side of the monitor, but I don't think that would be particularly elegant. So I think I'm going to put them up here. As always, I'll put down a piece of masking tape to mark my holes. That way if I mess up, I can just put a new piece of tape on there. I like all my stuff to line up nicely, so I'll start with a straight line. Then I'll mark 4 spots that are 15 millimeters apart. And then I'll use a tiny drill bit to mark a pilot hole on each one. After that, I don't need the tape anymore. And then I'll drill the larger holes. And, as you can see, perfect fit.
I like that milling drill.
Okay, so I've mounted the RCA jacks and toggle switch, and since I was not able to find any colored RCA jacks in time for this video, I'll just add a little label here for that. And this switch, of course, will enable or disable the RGB input. Now what's left to do is solder wires to all these things. And so skipping forward a bit, I'm just about finished with that. Now this is an entirely separate ribbon cable, so my plan is to place an IDC connector at the end of this ribbon coming out of the TV. And the goal is that I want to still be able to remove the back cover of this TV without having to desolder stuff. So I need a way to disconnect things. And so I thought adding this connector would work well for that. Unfortunately, I ran into a problem on the other side. I thought I ordered a pack of male and female IDC connectors for ribbon cables, but the male connectors ended up being for PCB mounting, not for mounting on a ribbon. And I didn't even notice that until just now. You see, I was thinking these would be just like the female versions where I could put the ribbon cable in. And since it could take several days to get these ordered, I decided to take a shortcut for now. I'm just going to plop one of these little guys here on my quad hands, and then I just soldered all the wires directly to these pins. And then, to make sure these don't contact anything inside the TV, I'll coat everything with hot glue. Now, I did order the correct replacement part, which I'll have in a few days, but for now, this should work. And so, as you can see, I can now take the 2 halves of the TV and connect them together, like this, before I reassemble everything. And now, I'm going to need 4 RCA jacks I can connect to my Apple IIgs. And I'm still going to use this little prototyping connector for the moment, as it's fast and easy, but ideally at some point I want to properly build a permanent cable for each of my systems.
I was just thinking of something else too.
And here's another annoyance. This cable set was originally advertised as being several feet long, and it's actually really short. Originally I planned to cut it in half so I could use it on 2 systems.
I've got a better
now
idea
it looks like
now.
I'll just need to cut these off
now that
the
I'm
end
watching
here.
this.
And so now I've wired all these into the video connector. And on the other side, I have red, green, blue,
So, I mean, I
sync.
do have
so
monitors that have RGB inputs.
And the
I do
sync
have a couple
actually
of
goes in
those.
the original composite port. Pity the cable didn't have a yellow plug to match. Okay, let's try this again. Okay, on first try, I got nothing at all. But then I thought maybe I mounted the toggle switch upside down. I have been known to do that. So let's flip it the other way. And try again. Yep, it works. Okay, so let's try some games. Wow, this looks really amazing. I want to show you some comparisons with composite mode. So I'll flip the switch back to composite and check out the difference.
Composite's a little brighter.
It's probably more noticeable on a close-up. So we're still in composite, and look how much cleaner it gets when I flip to RGB. So let's try another game. So again, we're in RGB now, and here's composite.
Oh wow,
zoom in a bit.
RGB is
Here's
cleaner.
composite, and now back to RGB.
Huh.
So let's try this Tandy Color Computer 3. It has a
I got
funky
that
RGB
too. He's
port
got the
on
old
bottom,
stuff.
So I constructed this little cable for testing, and I could probably make something more elegant later. So let's give it a try. It works. So again, let's do some comparisons. I'll switch to composite mode, and the text is much harder to read. And back to RGB.
Wow.
So let's try a game. Wow, this looks great. I've never seen a Tandy Color Computer connected to RGB before, and it looks like a whole different computer. It's really amazing. So here's another comparison, and let's switch to composite mode, and back to RGB.
Alright, so here's what we're
Okay,
going to do
well,
here. Let's go to search here. He said the VGA is an RGB connector. If that's true, we could use a VGA monitor, which I do have some. Yeah, it is. Look at that. It's got red video, green video, blue video. There's a horizontal sync and a vertical sync. See, what I was thinking of doing is using the 3 inputs on an RGB.
Hi, I'm Eric Naso. What I'm going to show you is how to white balance your camera using the waveform monitor in RGB mode. Here I have a really good size white card or foam core. This will help really show what it looks like on the waveform. I have the GH5 set to 3500K so that you can see what it's going to do when I switch it over. So let's go ahead and switch it over and we'll show you the waveform. Now this can be really handy, especially with the new OS3 on the small HD monitors. So you have some options when it comes to setting up your waveform. Now you go into the settings and here you can see that you have RGB, you also have Luma. That's great for when you want to really know how hot your image is or your highlights. And then you also have Parade, which is very handy as well for seeing color balance. And you can also white balance using this, but I prefer actually using the RGB because it gives you a much easier and a really precise visual of what it's going to look like. So here is what it looks like when it's not white balanced correctly. You see the red, green, and blue channels and they're just all over the place, right? They're completely spread out. So in order to make the image look correct, we're going to have to get those three channels that you see right up on top here. Those three channels need to combine. And when they combine, they'll turn white. So let's go ahead and show you what that looks like. So as I move the GH5's Kelvin temperature up, it starts to get a little bit better. Now see how it's combined and it's turning to a white solid line with a little bit of blue left there. So that means it's going to be skewing a little blue. If I go a little bit farther, then I get a little bit of red on the left side. But that's okay. You can kind of decide, well, what looks best to you. This is really pretty good. So now I have it set. Let's go ahead and take a look at the GH5 again. And I am at a 5700K. And now I have a really nice white balance. Well, I hope this little tip helped you finding another way to white balance your camera using the waveform in RGB mode. I'm Eric Naso. Thanks for watching.
Right now, why can't I just use the monitor to expose my image properly? And the answer is because your eyes and your brain can be fooled. External elements such as ambient color temperature or the brightness of the room that you're in can affect the way you see the image on the monitor. Not to mention, the monitor you're looking at may not even be calibrated properly. Using scopes is the only way to know for sure what you're recording. The histogram is essentially a bar graph that displays luminance. The brightness levels of the image are displayed along the x-axis with 0 representing pure black and 255 for pure white. The y-axis shows us the number of pixels at each brightness value that the image contains. This tells us if the brightness range of a given scene will fit the camera's dynamic range. If the entire graph fits between the left and right margins, we know we're not losing any information because no part of the image is too dark or too bright. If the image is aligned further to the left, that means there's an abundance of darker pixels and we may be losing information due to underexposure. But if the image is to the right, then we know we might be losing information due to overexposure. This is where it gets tricky though, because there really is no right or wrong histogram. Different subjects may be displayed very differently, but may still be exposed correctly. So the histogram is good for telling us the brightness range of a given scene, but not really where the values are falling. To quickly find out what parts of an image are reaching specific luminance ranges, we can use zebras. Zebras are one of the more common in-camera exposure tools. They work by laying a striped pattern over the parts of an image that correspond to a particular luminance range. Zebras can be set differently and are typically used to alert the operator to areas at or approaching overexposure. However, just as the histogram gives us an overall impression of the tonal range, zebras are only giving us a small snapshot of certain luminance values. For a better, more detailed representation, it's best to use a waveform. The waveform monitor is the most commonly used scope out there. It displays the luminance of the corresponding image using IRE values. IRE stands for Institute of Radio Engineers and is a unit used for measuring luminance. The y-axis ranges from 0 IRE, pure black, to 100 IRE, pure white, and anything above 100 is considered super white and is not broadcast safe. Now, unlike the histogram and zebras, we are seeing the full luminance range of the image and exactly where each value occurs, which leads us to our final production scope, false color.
False color is an increasingly popular tool for evaluating exposure. With false color, distinct color values are assigned to specific IRE ranges, allowing you to see every luminance value in the image at a glance. It's very similar to the waveform in terms of what it's displaying, but rather than filling a graph, which requires a certain amount of interpretation, false color just overlays your image. This is also great when evaluating the contrast range of an image, as you can quickly and easily see what sort of ratios are playing out in the scene. Scopes are not only useful in production though, they're indispensable when it comes to post-production. Evaluating the footage and normalizing any differences in exposure or color across scenes is what color correction is all about. And since we know we can't trust monitors, but we can trust our scopes, understanding them is vital to a successful workflow. The RGB parade should look fairly familiar. It's essentially a waveform. But instead of viewing luminance, we're measuring saturation from 0 to 100 of the red, green, and blue channels. Each section of color represents the whole image from left to right. The y-axis is still measured from 0 to 100 and represents that particular color channel's saturation. For a well-balanced image, each of the three colors should be roughly equal. The vector scope is excellent for precisely matching color between shots, while ensuring that the colors are not over or under saturated. It's laid out like a color wheel. We have red, blue, and green, and we have magenta, cyan,
they don't
and
show
yellow.
it in use, you know?
The distance from the center of the circle represents a color's intensity. Black, white, and neutral grays will be smack.
Hey guys, and welcome to another set. This is going to be an intermediate tutorial, and not only will I assume absolute black. And watch this waveform monitor as I scrub through my video. Can you see it's shifting a little bit, and it's obviously picking up, it's live updating with my preview window. And what I can see is there are a few spots here in the image that are absolute white, and if I look over here, that's actually these waves. These waves here are absolute white. If I were to color pick these values, it's absolute white. So it clips at 100, which is the maximum value. Over here, there's a little bit of brightness with some of the foam over the waves, which is these little blotches here. And then towards the left, it gets a little bit darker because we don't really have much brightness on the left side of the image. The other thing I can see as well is that this solid block here of bright pixels is actually my sky. So this is actually a fairly bright sky, but it's not maxed out. It's just fairly bright, so it spans across. And then all of this here is the land as well as the ocean. The waveform monitor is really great at showing you whether your image is properly exposed. Ideally, you would want the image to contain colors from the entire spectrum, from 0 all the way to 100, so you know you've got the full dynamic range to work with. I can see, however, that my image doesn't really go all the way up to black. There's a little bit of a gap here at the bottom, so my image is actually lacking a little bit of contrast.
Let's see what this is here. Camera, lens, vlogging camera, a 4K drone, audio recorder, shotgun mic, my software, Adobe Creative Cloud, video connector. See, now what I want to do, okay, now we're getting into a little bit more detail. Normal broadcast TV codes, VGA graphics, and normal broadcast, etc. Video signals you watch on TV screen are generally composite. Picture sent to. So what I'm thinking of doing is, you have VGA monitors. I'm thinking of adding each signal to a red, green, and blue, and then inputting that into an RGB monitor to monitor that 3D waveform. The H-sync rate of TV is 15 kilohertz per pound. Yeah, but monitors are... Alright, so you've got RGB input, ADD converters, sync controllers, sync DA, RGB, S video. VGA to TV converter. I'm not into that. That's what I'm trying to do. Well, I'm getting off the freaking tangent here. Talks about component video. So what we could probably do is we could look at the output of a signal, and then we could mix each of our signals to each of these colors. We could mix the signal somehow. I'm not sure how exactly we would do that. Damn, I didn't want to get into this. Back to this Chua circuit. Where was I? Yeah. And then there's the gyrator part. So anyway, here's the description of the Chua circuit. That's what it does. I was looking to see what they use for an op amp here. There's a slim possibility we could try to build it tonight. But I might go with that. I tried to build a LM324 oscillator. That didn't work out very well either. doesn't say in here what they're using. It doesn't say what they use for components or anything here. So there's some examples of negative impedance circuits. So we could actually vary the circuit itself. Like here on the negative section, they've got R equals 220 ohms, and here it's 22K. Oh, these values are in here. Where did I get this? Is that the same numbers? I think it is. Oh, this one doesn't show. Just trying my values. Oh yeah, it shows it there. That's where it is. We could substitute things in here for different types of negative impedance diodes. These are all 1K. It's a 22 microfarad. God, you'd think I'd be able to build this, wouldn't you? I don't know what the voltage is. Ground. Where's the supply? I think you just turn the supply on. I don't know what they're using here for. Now, in one circuit, they separated. I think they even used two different supplies for the two different circuits because they were interacting with each other. And this is the 3D to 2D conversion. It's glenstuff.com, GLENSSTUFF.com. Yes. And it talks about quite an elaborate circuit to convert everything from 3D to 2D projection on an oscilloscope. Now, maybe we don't need to do that. I mean, we can still look at each section here. See, you can look at, these are all 2D views. There's the X rotation, you know, X, Y, and Z separate versus time. I suppose if we just had one of those on the scope, you know, we could get away with it. And that talks about the whole, this is a sine, cosine potentiometer type of a thing, which there's another circuit here. This is a more complicated circuit. It's using A to D converter and TLO81s. I don't know exactly what they're trying to do here with these A to D converters. I have no clue what they're doing with this. More A to D converters. I think they're just adding signals together to create those waveforms. I don't think this is the actual Chua circuit. I don't know what this is. I really don't. There's noise circuits that we want that I wanted to talk about. We have to get into building noise circuits, noise generators, and there's what's called stochastic resonance, which maybe that's what I was trying to get into. Stochastic resonance is a phenomenon where a signal that is normally too weak to be detected by a sensor can be boosted by adding white noise to the signal. The frequencies in the white noise corresponding to the original signal's frequencies will resonate with each other, amplifying the original signal while not amplifying the rest of the white noise. So you could add white noise to a signal. Okay, let's say you had let's see if we do this here. Just put this inside of my viewer. Let's see if you had, okay, so you've got the noise signal, let's say, and alright, so say you've got the noise signal coming in, okay, so that would be represented by the blue line. Alright, so let's see, we have another one here. This is your white noise generator. So it's providing, you've got this circuit now. Okay, now you have your input circuit, okay. This is your we'll call it input. And this block here this adds your input. Okay, so now you've got, then on the output you've got your blue, you've got your green, so you've got the blue and the green, and then along with the blue you've also got, you might have this stuff, okay? So then what you would do is you would create another box. Now you've got your blue and your and this here, okay, you've got these two. So then what's going to happen is the two blue signals that you've got going in here that are referenced, you got your reference signal and whatever in this combination. So then these two will come out, they will come out, the noise will cancel, and we'd probably have to have we would have in here what's called group delay or delay. And so what happens is you've got a signal that's coming in here, let's say we call this a noise, and at the same time, oops, now what's going to happen is the time between these two circuits is going to be off. So what you got to have is a delay there's going to be a delay function, like this is going to be delayed. Let's see, we could do we could say that the function is delayed by, like, let's say it's delayed by 180 degrees. So then you would have (180°) phase shift for example. And you would have, this would be a tuner. We could make it let's see, we could make it green. So this would be part of this whole circuit. So you're delaying, you've got this variable resistor or variable impedance, we'll just call it VZ or something, V, I guess, V sub Z. And then so you're varying the impedance so that you can match this. And how we would actually do this. Okay, so how we could actually do this is we could take a pilot tone. Okay, so let's say we grab a yellow signal. Let's see here. And this is going to be these are called pilot tones. And what they are used for, they're used for testing signals. So you can't, when you do this group delay, if you've only got noise going through there, you can't adjust the phase so that you've got a signal, you've got one signal you've got another signal here. And you want to get a phase so that's going to be equal to the total. You want to cancel, okay, so you get 0 volts, 0 volts AC on the pilot tone. So this is your pilot tone signal, this is your test signal, and you run that through your noise and your group delay, and then you combine. Then once the phase shift of the system is set, then you can take off, you can turn off the pilot tone. And that's how you do a phase test, and this looks complicated, but it's really simple. That's just and I could save that later. But so that's the way we're talking about adding noise and to signals. I don't know. Let's see. Let's see if there's anything else here. See, I was looking at this picture. And I'm thinking not only in terms of audio for the interdimensional communications, but also for video, and maybe combining audio and video. The original is modified by the addition of noise and carrying out of a nonlinear threshold operation. Each panel shows a different level of noise variance, with a standard deviation of 10 grayscale levels in the top left, 50 on the top right, 100 in the bottom left, and 150 in the bottom right. So they're adding noise to this in order to get your picture. It's pretty cool. So, and there's this theory where we add noise to these energies. These entities use noise, and here's a stochastic resonance peak. So stochastic resonances have peaks, I guess, and valleys. So here's the thing. This is what I'm trying to get at, okay? So what we're doing is we're taking the apparent chaotic signal, which looks like noise, and we're adding that to the circuit. So we've got a white noise generator, or we have chaotic noise. So in the same situation, we can take that signal and we can run this all the way through in the same way that we did for the regular noise. And we should be able to add a pilot tone to that as well. And see whether or not the pilot tone becomes inverted. So here it's 180 degrees out of phase, so then your result's going to be, actually it's going to be cancelled. It's going to be cancelled. Let's see if we can just get that. Let's see, here we've got so once the pilot tone goes through the system and the group delay is done, the pilot tone, the group delay is set here so that the resultant wave, actually I did that wrong. I did that wrong. This is supposed to be in phase with the input, okay. Alright, so you've got let's put a blue marker here. And then back to the original on the output here on this time delay. So then at the end you have a zero wave like that. That's your pilot tone. Now once that's set, because both of these signals are going through here, see? So now you've got your group delay set, you've got the noise, whatever noise is going to come through here is going to get cancelled. But at the same time, that noise is going to amplify this signal, and that's going to be amplified, I guess. I don't know. I don't know. There's good stuff in here. Let's figure that all out. Now see, this looks almost like chaotic. Oops, that page can't be found for web figures. Alright, so anyway, we've talked about that to death. Let me jump ahead here. Alright, let's look at this guy's circuits. Series circuits out of parts and price electronics. Go shopping. So he's using two TLO82s for the op amps. He's got linear taper resistors, not non-linear. Non-linear is your audio. I only have 1K resistors. Breadboards. Is that the thing I was looking for? Yep. I'll be damned. I got this. And I've misplaced it. and that's a stereo input, so you can hook it up to your computer. That's what I wanted to do. I got that thing around here somewhere. There's the potentiometer wires. Sound card oscilloscope. Sound card oscilloscope. Let's get a regular oscilloscope up there. Here's the sound card oscilloscope. We looked at the other one.
Hello? Today we'll be hooking up an analog chaotic circuit into our audio card scope, also known as the 4-man
I
scope.
don't think I'm going to be able to get to this tonight. I'll have to wait
Let's
till this
begin
weekend.
by connecting the sound card into the USB slot of our
There's
laptop.
that UCA device down there.
One of the first things to always check is that the analog input is not the microphone of the laptop, but the USB sound card itself. And here I have to change that. We go to XY mode, and now you can see as I'm speaking, we no longer peaks. Let's connect the probes. Here I connected the probe to a 1 mega ohm resistor that will connect to C1 here and C2 here, and of course we will connect ground. And turn on the power. See, first we have nothing. We have steady state. I'm changing the parameter. Turning, turning, turning. Still turning. Still turning. And we have something. Let's go back. Here we have a simple oscillator.
Yeah, that is
Forward.
awesome. Look at that.
Here I tuned it again. We have the first bifurcation. Let's try to get the second right here. And beyond that, it's difficult. I'm going to keep turning.
Oh, look at that. Oh my god, that is awesome.
This is the Chua's oscillator.
That is awesome.
Let's see if we can get bifurcation by changing the second parameter. Turning it back, back, back. Steady state. Simple oscillator. Turning, first bifurcation. Here we get the second. And then we have chaos.
Pretty cool, huh?
Thank you.
That is very cool. They're showing the circuit board, but they're not showing the. It's a TLO82. They show that setup there, but they don't. She's not showing the schematic diagrams. It's the schematic diagram itself. I want to see the schematic diagram. I'm assuming it's the same. I don't know. Let's see what we got here. Sound card oscilloscope. Download the latest version. Oh, cool. That looks cool. We'll download that. That's a good picture there. See, there's a capacitor there to ground. There's a capacitor there to ground. That's those two capacitors. And they also mentioned these are not mica capacitors. They're the... I got a crap load of those capacitors. I'll show you one. I might even be able to do this. I don't know. I found these... one of my boxes. I've got another box somewhere, but let me just go over here. Just do this here. Real quick. So if you look down inside this box, and of course my headset's going to disappear on me. I might try to... I mean, I don't think I have time to build this thing tonight. I don't know. I have to get up in the morning again. But you can see all the components in there. Let me, if you look real close here. This is an example of the Mylar, I think it's called. This is your Mylar capacitor. They're shiny. And the ceramic capacitor, like here's another one. This is a red one. I've got tons of these red and green capacitors. They're real shiny and smooth. The other one, where's that damn ceramic? This is the ceramic capacitor. They're round typically, and they're not as smooth. They've got kind of a rough surface. But that's a box of goodies. God, I got my stuff running over there too. I forgot all about it. It's not really doing anything, just sitting there. Looks like two of those capacitors are the same, aren't they? And we talked about impedance bridging, RGB stuff. Probably deal with that later. Pretty cool stuff. Circuit. See, they're using plus or minus 15 volts, and I have, these are different circuits. This is the circuit right here. So there's a 22 microfarad and a 220. There was another capacitor in that circuit. 22 right there. 22 microfarads? It's not polarized though. Am I going to get a capacitor that size? It's not polarized. Oops, sorry about that. Back my... Let me see. Let's see if this is basic components. Here's your power supply. Tools, materials. Oscilloscope, 4-man scope. make sure that the ICs are not hot, because they tend to get warm. They use up a lot of current. That's why I've got plus or minus 15 volts. Those capacitors look small there. Oh, they've got another set of resistors going to the jacks, going to the output jacks. What are those? One megohm resistors. That's to limit the current. A bag of 500 resistors. Oh. Those are 10K pots. You'd think you'd have a schematic diagram. He's got an LED for the power supply. He doesn't show the circuit. That was 3 years ago. Let me go into this parts here. 2K, 220, 22K, 100K, 1K, 3.3K. Got large resistor capacitors here. 22 microfarad and 220. I don't see that in this circuit anywhere. Doesn't say anything about his capacitors. He's got 0.01 and a 0.1 capacitor, film capacitors. He didn't use these other ones. Used a 0.01 and a 0.1. I'll talk about noise generators some other time. There's a 324 I wanted to build. wanted to get into pulse width modulation. I'll just put it there for now. Let's see. How to play with chaos. This is the whole superposition theorem.
Hey everyone, Sam Ovens here, and in today's video I want to explain how to play. You know, you've got initial conditions for when your company was formed, right? So when you form your company, the first few
there's a lot of discussion on this. It's like there's hardly anything really. Photon, beta, stability, chasers, chaos by multisim. This guy used an Arduino. Music. I don't know what that shit's all about. To simulate a chaos circuit. Well, we're not simulating, we're actually creating one. There's a simulated circuit. Oh, this is the one with the two diodes. This is the one with the two diodes. Let me see what chip that is. That's a 741. I got those diodes. It's a variable capacitor. Plus and minus 9 volts. Just added to that those diodes. Just put 9 volts there. I could almost build that one. What if I could build that? I don't have take 1 2Ks 4 nanofarads. That's 4700 picofarads. Alright, those capacitors are. Oh, that's a variable inductor. He's got a variable inductor in there, a variable 8.5 millihenry. I can't do that because I don't have that inductor, but maybe we could. Well, let's just look and see what else is in here. There's stuff in here. I'm wondering about inductively coupling this circuit. See, there's the 27 millihenry inductor, but this isn't the one with the 2 diodes. Oh, looks like they're measuring the voltage. They're doing a separate voltage measurement across that resistor. There's the one with the 2 diodes. They've got 15 volts here. See, with the L1, all we'd have to do is put in that gyrator circuit. They're using LM358 on this one. Ooh, look at these. I like these. LM358, 290 ohms. So I'd have to simulate L1. And L1 is simulated right here. Probably use another LM358 or something. And then in place of that, you know, we ought to just see if we can do this. I mean, it's 12 o'clock. God damn. I think it's too late. I don't know. So that's the circuit we're going to build. Let me take this thing off. What I'm going to do, I'm going to grab me a little drinky poo and a little snacky poo, and we're going to see if we can get the parts and throw that thing together. I don't think it's going to work. You know, I want to turn off. Oops. I'm going to turn this stuff off here. Now, I have another supply. I don't think this is LM358. Ceramic capacitors. What the hell happened to the... Oh, God. No, no. There's another wired core thing that I tried to build. This thing's got all kinds of crap in here. I don't think these are LM358s. I'm almost certain they're 4-pin chips, 8-pin chips. Yeah, I don't know what that shit is. Maybe the capacitors. Probably these stupid 104s and 103s. I have no idea what they are. Yeah, that's what they are, 104s. I could probably measure them on that thing, couldn't I? Let's pull off all the wires on this. This is my prototype board. And because it's a brand new board, and the other one over here, I'm going to put this stuff together and probably just I'll leave it because the pins on this other board are pretty much gone, I guess. I don't know. My bird's like, That's reading 103 nanofarads, so I can read I got a capacitance meter. That's 0.1 microfarads. So I've got a 0.1, which is 0, so I need a 105. That's a 0.0047 microfarad. Cowabunga. Wait a minute now. I've got some other crap over here somewhere. I know I had a 103.47. That's a 0.2 microfarad. This is... That's just 2 nanofarads. Wait, point? What the hell is the other one? A 100 nanofarads. That's 2 nanofarads? That's 0.002 microfarads. 0.1 microfarads. 0.002 microfarads. That's a lot smaller. Wait, yeah, I need a 0.01 micro. What's this guy right here? What's this guy? Is this what I want? There's the 105. This might be the puppy I'm looking for. .7 microfarads. Holy cow, there's something wrong with that one. I think there's something wrong with that boy. 0.7 microfarads. That's a 0.1 microfarad. Those are all like 0.1. Shit. I think we got a winner. Wait a minute. That's 0.001 microfarads. I need a 0.01. I might have some in that other. That's a 0.1. What is this? One microfarad? That's a 0.7 microfarad. Maybe I could just throw that in there for now. Alright, so we need a 1.8K resistor. I got some 2K resistors in here. I had a 2.2. If I used... Where did I see that little bastard? I know I got a lot of stuff in here. It's freaking crazy right now. It'd be like that's 100 ohm. There's a chip that died. I'm just kidding. What Where the hell did those 2K resistors go? I just had them here. That's a 1K. I'm gonna need a bunch of 1Ks, come to think of it. I need 3 1K resistors. And I think I have 3 1K resistors. There's one there. Wait, yeah, that's a 1K, I think. That's a 1K. I got 3 of those. I need a 22 microfarad. I don't know where the hell I get the 22 microfarad. They're using different values. There's a 70 nanofarad. That's a 0.07 microfarad. 0.07. It's close to a. That's close to a 0.1. It's probably closer to a 0.1 than the other one. Let's put these over here. This would be our 0.1. And the 0.01 is going to be over there on that side. I'll need another 0.01 over here. And I've got the 2 op amps. I need a 1.6K resistor. 1.6K. Those are going to be hard to find. .6K, 2K resistors or whatnot. I gotta move this over, put this over here, so I can peer down in my thing here. And I need that might be a 2.2. If I do a 2.2 in parallel with a 2, that gives me 1 something. We need some 1K resist, another 1K resistor maybe. There's a 10K in case I need that. Oh God. There's a, that might be a, I don't know, what the hell is this here? That's a 2K. See, if I put a 2K in parallel with a 1K, that's going to get me 0.6. So I could put those in parallel and add another 1K and I'd have my 1.6. So I gotta find some 1K resistors in that pile. Another one. And I've lost my tweezers. It just disappeared. I can't find the tweezers. Did I drop them? What the hell happened to them? I ended up over here. Let's see, let's turn this stuff off. 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 I don't need that on. There's 100K. There's 100 ohm. That might be a 1 meg ohm. What is that actually? Let's see. Let's take these. Put that right there. That's 100K. That's 10K. Need some 1K resistors. There's some 10Ks in there. There's a 2K. If I put a 2K in, bunch of 10s. I love this job, I swear to God. I love doing this shit. There's a 1K. I think it's a 1K. 3 1Ks. I need another 1K resistor. Oops. There's a 1. That's not a 1K. It's a 2K. I need that. I don't know. There's a 1K right there. So if I take this 1K and put that in series with these two in parallel. Well, it would have been nice to put this guy over there. There. And that gives me 1.6K. So it's a little bit off, but that's okay. So there's the 1.6K. There's these two in parallel. That one in series. And this 2K. There's my glasses here. There's the 3 1Ks and the capacitor. There's all the components for the gyrator. Now I need a 22K and a 200. Wait a minute, he didn't use those values. He did not use those values, did he? What's he got here? Let's go back over to the circuit. So this is what we're building. We're going to build this Chua circuit with the slight modification, I guess. Here they're only using 1.01 and 1.1. Where in the hell are the other capacitors? The 22, no, I don't use that. Oh, he's got a variable resistor here. Or 5 or 10K linear taper resistors, 2 of them. Where did he put those? I have to look at that circuit board. Oh, what about the op amps? Oh, he's using TLO 82s. Ooh, okay. Can find those. Where's he putting the 5K resistors though? Okay, he's just using... Oh, he's got it in parallel with... He's got one of them in parallel with the resistor that's connected between the two. And the other one is connected from ground to some point on that other chip. 220s, 2.2Ks, 2 2s, and 3.3s. That's a 3K. Where's the 3.3? This isn't the same circuit he's using. He's using something different somewhere. There's a 3.3K and a 390. But that's on a LM358. Interesting. This is the same circuit that's over there. I don't know. That's as close as up as I can get to see that board. TLO 82s. That looks like a 22K. Oh, you see, he's got that resistor. That variable this is open, and that variable resistor is connected in parallel across this one. There's the output. There's the capacitor there, and there's the capacitor there. These two look the same. All three of these look the same. I don't know what he's doing. Oh, this was the other. Maybe he used this one. Yeah, see, these are 100 nanofarad, 10 nanofarad. Okay, so that's different there. But where... Let's just back this up. R is a 2.5K pot. Where is R? This looks... This is the gyrator here. Okay, C is 100 nanofarads. I got that. R9 is a 1K. R8 is a 1K. R7 is 100 ohms. I need a 100 ohm resistor. It doesn't say that here. R7, 8, and 9 are all 1K resistors. And C3 is a 22 microfarad. So something got changed. Something got changed somewhere. This was in 2007. I'm assuming this is a better circuit. So R7 is a 100 ohm resistor instead of a 1K. So let's change that. We're going to use... Oh, and R is a 2.5K pot. Okay. That's what he built right here. This is what he built. So we got to have a 100 ohm resistor. And I think I just saw that in there. I think... And I got the TLO82s. I got a feeling I'm going to be building this sucker. I think we're going to be building this sucker tonight. We might not see the display, but I think we're going to build it. Because I got TLO82s. I got a crap load. I'm just going to find me a 100 ohm resistor right there, I believe. So, they're building from that web page. That's 100 ohms. Alright, so I've got 100 ohms. I've got that good stuff. I got this guy. Wait a minute. What about that 1.6K? Now, where the hell did I see that now? R10. See, I think this circuit's backwards. I don't know. We're gonna go with this layout right here. R10 is a 2.5K pot. R is a 2.5K pot. So I put a 1K 1.6 valued resistor in there. So what we could do is we'll just take what if we take 1K. We'll take these guys out of the loop here, and then I'll just put a variable resistor in there. I got tons of variable resistors over there. It's actually better if I have a smaller valued resistor for finer control. And we can do that. We can put finer controlled resistances in there. Okie dokie. Alright, we got that. Oh good. I'm just so good at this shit. We're actually putting this together. We need 220 ohms, 2.2K, 22Ks. Alright. That's a one. I may have to put some so I'm looking for the reds now. I'm gonna have to look for them special somewhere. There's a red, red, orange, red, red, red. Okay, wait, I got a whole pile here. Let's see what we got here. Red, red, red. I think that's, I don't know what that is. We'll find out very shortly. That's a 2.2K. So there's a 2.2K. I believe it's on the other side of the circuit, so we'll just put those over here. I need 2 of those. $2.2K. Wait, I only need 1. Oh shit. Well, let me just shove this back in a little packet here. Probably can't do it now because I pulled that out of there. I got that one in there, okay. And I got that one in there. Alright, we need a 22K, don't we? That's going to be red, red, orange. I may have to go look for... That's it. I need red, red, orange. That's red, red, red. Wait. 2.2K, 22K. I need red, red, orange. I may have to look for that in my box. There's an orange, orange, orange. That's a 33K. We need that. I need a 3.3. That's a 3.3. That's a orange, orange, red. I need a red, red, orange, and an orange, orange, red. Let's see, that's red, red, purple. Red, red. That's a 2.2. I think I gotta go to the box. The box is buried, of course. It's challenging. There's some resistors in there. I'm gonna need. Let's see what's in here. Might have something in here. There is a 100 capacitor in here. What do we got? See, I got all my diodes in this box. Those are all red, red, reds. Orange, orange, orange. Yep, I don't see them in there. There's some interesting capacitors in there. There's a 10K. No, not in there. And I have to go somewhere tomorrow. I don't see, when I get motivated to do something, it's like I have to finish it, because if I don't want to get back into it, you know? Yeah, you think it's funny, huh, bird? I'll give you funny. Alright, here's my resistor pack here. And we need... There's a red, orange. That should be 22K, and I need 2 of those. It's 22K. I've got, what is that, 2.2? There's my 2.2, 222Ks. I need 220 ohms, R1 and R2. R1 and R2, no wait a minute, what the hell? That's a gyrator circuit. What are these, 2 gyrator circuits? Wait a minute, something's different here. Something's way different. Let's bring this over here. No, those are 220 ohms. And 22K. 220 ohms. Well, 220 ohms is red, black? No. Red, brown, I think. That's red, brown. There's a red, black. Those are all end in black. $220 ohms, huh? Red, brown. Where the hell am I gonna find them suckers? Shit. Wait a minute, what's this one? Red, something. Red, yellow. God. I don't have 220 ohms in this thing. I got red, green. That's like in the make red, brown, I think. Is that it? Or is that purple? I think that's purple. Wait a minute. What is that? can't even see. It looks like purple. $220 ohms. I found it. It looked like they were purple. And they're not matched either. I'm wondering about matching them. So I got the 220. No, I need a 3.3K. That's orange. Shit. Orange, red. That's another one I don't have. Orange, brown. Red, orange. Orange, red right there. Aren't you glad I came prepared? Yeah, this guy's prepared. He's got all his fucking ducks in a row, I'm telling you. This guy is good. I'm telling you, I've done this shit for a fucking living. I live in the fucking state where they don't have this technology anymore. It's all lobsters. Which is fine with me. I'd just soon eat a lobster than eat a fucking resistor any day. Alright, we need a couple of TLO 82s. I think I know where I can grab me a few of those. Let's see what's this pile look like. I gotta be careful with this black stuff. We use the brown ones here. Let's see, those are all TLO 82s. I'll try to use a matched pair. Those are IJG, so I'll use this one. Is it missing a pin? The fucker's missing a pin. What pin is that anyway? Pin 1? I gotta look up my TLO 82s, bro. TLO 82C Texas Instruments. That's pin 1. Where is the pin 1 is an offset. Probably don't need to worry about it. If pin 1 is an offset and I can't do anything. Wait a minute, let me look at let's see here. Oh, wait a minute. That's a TLO 81. TLO 82 is an output. Wait a minute, is this a dual? What the hell is this? ICC. Plus or minus 15 volts. Is that just a single amplifier? I think it might be. Or is it a dual amp? This is a dual amplifier. TLO 82 is a dual amplifier. So I can just use one side of that amplifier. Yep, that's what I can do. They use two different op amps anyway in that circuit in order to do that anyway. So that takes care of that idea. So the pin designations. Put this over the way. Now the connector is in parallel with that. I don't like shorting that out, but that's a 2K resistor, 1.6K. What if I used... Wait a minute, let me put this back in here. Alright, there's a 2K resistor. Wait a minute. Fuck. Let's use this 1K. We'll use that for the center. Fuck. What the hell did they use for the capacitors? So we'll go back and C1. Okay, C1 is 10 nanofarads and C2 is 100 nanofarads. I need a 10 nanofarad capacitor. That's a 70 nanofarad. Can we get two of those? Wait just a minute, where's that little pile? If I put two of these in series, I'm supposed to have a 10. What's this one? That's a 1 nanofarad. So if I put two in parallel, that's going to give me 0.1. What the hell? That gives me 115. So if I put this in series, it should give me half of that. That's 27. I need a 10 nanofarad. Let me grab one more of them little guys, because I think there's one in here. I don't know what this one has. Wait a minute, what's these? What's this? It's 100. I think those are hundreds. Another 1 nanofarad. .2. What do I need? Wait a minute. I need a 10 nanofarad. That's a 0.2 nanofarad. That's a 0.15. Oh, those are small. I need to grab another one of these green ones. Where did I see those other ones? Shit. I'm going to have to go look in that box. I bet I only need one more of them fuckers. Oh my god. That's a big one. I need a little narrow one like that guy, don't I? Dude, that's 100. Well, I got a lot of these. That's a 20. What's I think that's a 0.1 again. Oh, that's a 20? Oh. That's a 20? Two, two, three. I think we've got our match here. So I think there's another one of them in there. Shit! Wait a minute. What is this? Oh, you gotta be shitting me here. Wait a minute. What is that one? Maybe I can steal it off of this generator. That's a 104. That's a 104. That's a funny looking one. That's big and flat. That's a flat one. This one's got some bulk to it. How about, is that one? What the fuck is that? That ain't it. Oh, that's a nice looking capacitor too, and I need two of them. You gotta be fucking kidding me. I got another box. I wonder if they're in there. Oh, I think I found one. I got a bunch of other capacitors over here. Oh yeah, I got tons. I got tons. That looks like the winner right there. Wait a minute, that ain't... That one might be it right there. I think I found one. So all I've got to do is just measure that one out. Yep, now I'll just put those in series. I mean, it'll be close, you know, like 22 or something. I mean, 12 or whatever. 10.8 is close enough for me. So I've got those. God, I got so much to figure out. Damn it. Nanofarads. It says I need a coil, but I can do the other. I want the 1Ks over there where this guy's gonna be sitting. God, I can't even get... What the... Fuck. There's a TLO82. Now, where the hell are the 1Ks? The 1Ks are in the 100 is 7, 8, and 9. So the 7 and 8 is a 100 ohm and a 1K in series. That's a 100 ohm. And that's in series, and that's connected to the inputs of that. The 100 ohm goes to the plus. Oh, these are dual. I can't use that chip. Damn it, I can't use that chip. They're using 4 op amps. Well, I'll just grab that one. Fuck it. Out minus in plus in and minus VCC. I don't know if I have time to put this together. Messin. It's just that's a 1K. The 7 is connected to the plus. So what I can do is go, there's the plus. And the minus is connected to R8. So I can go back to there and connect to there. That takes care of the first pair. Then I've got R9 is a 1K, and C is 100 nanofarad. Pretty sure that's what this is. I guess I better measure it. Okay. Now I gotta do the other side of this. The C goes to plus. So the other side is plus, minus, and out. So plus, and I need a 1K. Minus 1K minus the output of that combination goes to the split of the first two. Out minus, and the output of that goes there, and the output of that one goes to the split of the resistor and the capacitor. And just to double check, it's minus, it's plus, minus, and out. So plus, minus, and out. That goes to these. The outputs are connected, that's all connected. R10 is going to be a variable, that's 2.5K. I'm going to use a 1K. And that goes in series with a pot, and that is the plus side of the capacitor. So that goes there. And we need, I'm going to use my, what do we got here? I need a, these are like 10, I don't know if I got any 1K pots. I didn't do any 1K pots up. Oh, there's a 1K. That's a 1K. That would only give me, what the hell is this one? I don't even know what the hell that one is. That's a 5K pot there. That's a 5. That's a 50K. That's too big. I'm going to have to use this 5K. We'll use the 5K on this one, I think. And that goes to ground. And ground is going to be ground. Ground is going to be ground. Because we're going to have a plus minus voltage system. So I'll put ground in the middle. And then I've got to have C2, which is 100 nanofarads to ground. Wait, that's the 1K resistor. That's where the 5K is going to go in parallel with that. That would shunt it to 0 though, wouldn't it? Why is it in parallel? Fuck. Yeah, I guess it doesn't, no. It's a 5K. That should be the 5K. Something ain't right, because that value is supposed to be a 2.5K pot. Let's take this out and put the 5K pot over here. And I'll put this guy over here. It's a long ass freaking wire. That's going to be to go from here to our ground point. Our positive 15 volts is going to come over from here. Oh my god, I can't even get that fucking wire in there. There's that one. There's that one for positive. There's this green one. Green for ground. And that's going to be right here. That's our ground. Now I need a one for the Now I've got to do the other chip. I have to have C2. Has to be 100 nanofarads. That's this guy. And that goes from the first resistor to ground, which is here. I may have to put another ground wire in there. Get ground there. Ground there. I need another 100, no wait a minute, C1 is a 10 nanofarad. Now I used 2 of these in series, and that's on the other side of the resistor, which is there, and I've got to run those babies to ground. There's 1, 2, and ground. Where's ground? That's connected, and I go from there to a bridge between R1 and R4. R1 is 220 and R4 is 22K. That's 220. So we've got to go 220 ohms. Is R1. R1 is from the positive to the output. Positive to the output. So that's going to be number 1. So that means pins 1 and 3 have this guy across it. Pins 1 and 3 and 220 R4 is on the other one between the output and positive, and that's those 2 wires. I don't like the way that's in there. Wait, no, 3. Okay, I got those 2. Now I've got to do R2 and R5. R2 is 220 between the negative and the output. On the negative output on the first one. Oh, that's right across those. God. Wait, that was from. What the hell did I just do? From plus to the output? I did something wrong. It's supposed to be plus to output. I didn't do that. I went from plus to VCC. There's the output. There's this resistor, and that goes to minus. And that's like over there. Oh my god, these resistors are all bunched up here. Really weird looking. Minus to output. And that one's from plus to output. Now I need what the fuck? I did something wrong. That's a 220. That isn't right. Wait a minute. It might be. R1 and R2 are 220 ohms. Yep. R4 and R5 are 22Ks. I don't know what the hell that one is. That one goes from minus to output. Why do I have it's 220? Those are 22Ks. Why the hell do I have a that's a 2.2K? Those resistors are in. I need R3 and R6. R3 is a 2.2K. R6 is a 3.3K. So the first one goes from minus to ground. $2.2K. That's this one, I think. Minus. To ground. Minus to ground. That's plus minus out, and the other R6 goes from minus to ground. R6 is a 3.3K. Now what the hell is that resistor? .3K right there. Wait a minute, that goes from minus to ground. That's the second pin to ground. Now how the hell am I going to get that over there? What if I take this guy here, move this guy over here, let me go for now. Second pin. To ground. All of that is good. Those two are connected. All I need is a wire from there to there. R1 and R4 is 220 and a 22K combination. On the plus side. No, wait, they're supposed to be connected. R1 and R4 is supposed to be connected together. That's just connected to ground. The two pluses are supposed to be connected together. R1 and R4 is a 220. It's on the plus. That one's connected to ground. That's a 2.2K. Wait a minute. It's it's the 220 ohm. Wait a minute, did I do something wrong? Those are the 22Ks. R2 and R5. Fuck, I'm confused. Both the 220s, R1 and R2, are on the same side of the board. The R2 that's connected to the minus has to have R3 to ground, which is a 2.2K. And that's where that is. And the other minus goes to ground, which is what I just did. R1 is another 220 ohm, which is supposed to connect to... I just have it connected to the plus for right now, which is that one. And then the output is, those are connected to that, but the other side of that plus side has to have a connection to the other plus side on the other side of the chip. And that's that first pin. So there's got to be a wire that goes over there. So I connect... Wait a minute, where the hell is it pluses? Pin 3 to pin 5. Uh-oh, what the fuck? Yeah, there's pin 3. And that's pin 5. Pin 3. Pin 5. And that connection has to be connected to the other end of the resistor. Which I could just connect it to the resistor. Well, actually, it's connected to this other capacitor, the smaller one? No. That's the 100 nanofarads. The 10 nanofarads are on, it's on the other side. That's C2. C1 is 10 nanofarads. That's the small ones. So all I have to do is connect a wire from there to there. I just had that yellow wire in my hand. Damn it. I don't know where the fuck it went. We're almost ready here, believe it or not. Let's fire up the scope. Use a brown one, I guess. It's kind of a long wire. So I go from there to there. Now I connect my VCC. I got a crap load of them fucking wires to connect. We're running this on plus and minus 15 volts. Minus is 4 and plus is 8. Where the hell is ground? Is there even any ground on these chips? There's no ground. Ground is just where the other stuff is connected to. Ground. just plus and minus. That's plus. My minus VCC I put over here. Which, you know what, I'll tell you what, let's put this over on this rail. That's minus. This is plus. And another minus. Of course, that's going to be screwed up, isn't it? No, I'm just going to use whatever I can find here. That's minus. Now we need a plus. Ladies and gentlemen, we have built our first real live Chua circuit for chaos theory, and it is an hour and a half past my bedtime. This is on. I need another set of wires to go to my scope. Now the measuring points are across that variable resistor, the first one. So, and I have to go to XY axis. Oh, how the fuck am I going to do that? I can measure each one separately to ground and just see if there's some activity. There's a ground there. Oops, there's a ground there. And the resistor. Seems going to pull everything out of its fucking slot here. Alright, I'm measuring my power supply voltage. I've got the scope turned on for channel 1. This is the excitement. This is what it's all about right here. You might not think this has anything to do with interdimensional communications, but it has everything to do with it. Let's see if something blows up. I've got 2 adjustments that I can make. I'll leave one sort of in the middle there. And we'll leave this one in the middle. Now let's see, now I've got my power supply is down underneath here, so all I gotta do is turn this on real quick. And here we go. We've got 15 volts. Nothing's hot. I have nothing on the scope whatsoever. And honestly, I'm not surprised. I'm not surprised at all. Oh, you know what could happen? You know what could be happening? The ground on the scope could be doing something to the circuit. Fuck. How the hell am I supposed to do that now? There is an XY mode. I can take, well, my power supply is good, so I'll take this off, and we will try to connect this to that. I'm not surprised that it's not working. It's just too much to expect, you know. It's possible that the ground from the scope is shorting out the circuit, but actually that's a ground. Now this is going to be the other part of the circuit. And that's ground, and we will measure across the other side of the resistor. Where the hell is it? There's that. Let's go to XY mode. We're now in XY mode. Let's see what happens. There was some activity, but it's not doing anything. Oh, something's happening. It wants to start. I think it wants to start. It looks like it's doing something, but there could be some interaction with these wires. Something is happening, but it's only happening on one channel. That's just a sine wave. There's a sine wave there. That's just my yeah, I don't like it. I don't know. We'll have to check everything tomorrow, another day or something. I built it, but it's not working. So it's called par for the course. It's a very complicated circuit, and you know, to expect it to work first time around, it's like, well, I guess it's not going to happen. So we tried, but we won't give up because it's a starting point. It's a challenge. It's a major challenge.